Hello and welcome back to another gentle exploration of the mathematical world. I'm so glad you're here with me tonight. Wherever you're listening from, whether it's tucked beneath warm blankets in a quiet bedroom, settled into a comfortable chair by a window, or perhaps curled up on a sofa with the soft glow of evening light filtering through, I'd love to know where you are. Feel free to share it in the comments. It's always wonderful to imagine this little mathematical journey floating across different spaces and time zones, like numbers drifting through the quiet hours. Before we begin our exploration tonight, if you find these gentle mathematical wanderings helpful for unwinding, or if they spark your curiosity about the hidden patterns in our world, I'd be truly grateful if you gave the video a like or even subscribed. It helps keep this channel growing, much like the mathematical concepts we'll explore together. Tonight, we're going to delve into something that touches every moment of your day, even when you're not aware of it. Calculus, but not the intimidating calculus of textbooks and exams. Rather, the living, breathing calculus that describes how your coffee cools, how your heart beats, how traffic flows, and how the seasons change around you. I hope this exploration helps you drift towards sleep, with a deeper appreciation for the mathematical poetry hidden in ordinary moments. But fair warning, if you find yourself staying awake because these ideas are too fascinating, well, at least you'll wake up with a richer understanding of the mathematical universe surrounding you. One gentle reminder before we dive in: this video is for educational and relaxation purposes only. We're here to explore ideas, not to replace any formal mathematical education. If you're studying calculus in school, please continue working with your teachers and textbooks. So, take a deep breath. Let your shoulders relax, maybe dim the lights just a little, and let's gently wander through the beautiful world of mathematical change. It began with a simple question that has puzzled humans for millennia. How do we measure change? Not the change of seasons or the change in our pockets, but the precise, mathematical change that governs everything from the arc of a thrown ball to the growth of a forest. Long before anyone invented the word calculus, ancient minds were wrestling with problems of motion and change. The Greek philosopher Zeno posed his famous paradoxes around 450 BCE, asking how Achilles could ever catch a tortoise if he always had to travel half the remaining distance. It sounds like a riddle, but it was actually wrestling with the concept of infinity and continuous change. Imagine watching a leaf fall from a tree on a still autumn day. At first glance, it seems to fall at a steady pace, but if you watch carefully, you notice something more complex. The leaf accelerates as it begins to fall, then seems to slow as air resistance takes hold, sometimes catching updrafts that make it dance sideways before continuing its descent. How do you describe that motion mathematically? How do you capture the precise speed at any given instant? This is the kind of question that mathematicians pondered for centuries, knowing that understanding change was key to understanding the world itself. The breakthrough came in the late 1600s, when two brilliant minds, working independently on opposite sides of a bitter political divide, discovered the same fundamental truth about change. Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany both realized that to understand change, you had to think about it in an entirely new way. Instead of looking at change over large intervals, they learned to zoom in closer and closer, until they could see what was happening at a single instant. It was like having a mathematical microscope that could examine the very moment of change itself. Newton was motivated by the cosmos. He wanted to understand how planets moved in their elliptical orbits, how comets traced their paths across the sky, and how objects fell toward Earth. The mathematics available to him could describe steady, uniform motion, but the universe was full of accelerating, decelerating, and curving motions. He needed new tools. Leibniz approached the problem more abstractly, fascinated by the geometric relationships between curves and their tangent lines. Both men realized they were looking at two sides of the same mathematical coin: the rate at which something changes and the accumulation of that change over time. What they discovered was that these two processes, finding rates of change and finding accumulations, were mathematical opposites of each other. This insight, known as the fundamental theorem of calculus, was revolutionary. It meant that if you could solve one type of problem, you had automatically found a way to solve the other. It was like discovering that addition and subtraction were connected, but far more profound. This connection opened up entirely new ways of understanding motion, growth, optimization, and change of every kind. The beauty of their discovery wasn't just in its mathematical elegance, but in its universal applicability. The same mathematical principles that describe the motion of planets could also describe the flow of blood through arteries, the propagation of sound waves, or the spread of heat through a metal rod. Calculus became the mathematical language of change itself, capable of describing any process where something varies continuously, and the remarkable thing is that this language surrounds us every day, quietly governing the world we inhabit. Consider your morning routine. When you pour hot coffee into a mug, the temperature doesn't cool at a steady rate. It cools quickly at first, when the difference between the coffee and room temperature is large, then more slowly as it approaches room temperature. This cooling follows Newton's law of cooling, which is described by a differential equation, a mathematical statement that relates a quantity to its rate of change. The coffee cup sitting peacefully on your table is actually demonstrating one of the fundamental patterns of calculus. Or think about the moment you step on the gas pedal in your car. Your speedometer doesn't jump instantly from 30 to 40 miles per hour. Instead, your speed increases continuously, accelerating at a rate that depends on how hard you press the pedal, the weight of your car, and the resistance of friction and air. That acceleration, the rate at which your speed changes, is the derivative of your velocity, and your velocity itself is the derivative of your position. The car carries you through a living demonstration of calculus in motion. Even as you breathe while listening to this, your lungs are performing calculus. The rate at which air flows into your lungs depends on the pressure difference between the atmosphere and your chest cavity. As your diaphragm creates this pressure difference, air rushes in, but the flow rate changes continuously as pressures equalize. The volume of air in your lungs is the accumulation of all those changing flow rates over time. Your body intuitively understands integration, even if your conscious mind doesn't realize it. When you watch the sun set tonight, you're witnessing calculus in astronomy. The sun doesn't simply disappear at a steady rate. The angle at which sunlight strikes your location changes continuously, creating the gradual transition from day to night. The colors in the sky shift and change as the atmosphere filters different wavelengths of light, and this filtering process follows mathematical principles that can be described using calculus. The gentle progression from golden hour to blue hour to darkness is a visual representation of continuous mathematical change. But calculus isn't just about describing what happens in nature, it's also about optimization, finding the best possible solution among infinite possibilities. When engineers design a bridge, they use calculus to find the shape that can support the most weight with the least material. When a bird flies from one tree to another, it instinctively follows a path that minimizes energy expenditure, tracing out what mathematicians call optimal curve. When your smartphone's GPS calculates the fastest route to your destination, it's solving optimization problems that would have been impossible without calculus. The more you look for it, the more you realize that calculus is everywhere, quietly working behind the scenes to keep the world running smoothly. The algorithms that recommend what you might want to watch next on streaming services use calculus to analyze patterns in viewing data. The climate models that predict weather patterns rely on differential equations to simulate the complex interactions between atmosphere, oceans, and land. Even the compression algorithms that allow you to stream this video in high quality use mathematical techniques rooted in calculus to efficiently encode and transmit information. Understanding calculus doesn't require memorizing formulas or solving complex problems on exams. Instead, it's about developing an appreciation for the mathematical patterns that govern change and accumulation. It's about recognizing that behind every smooth curve, every gradual transition, and every optimization in nature, there are mathematical principles at work. The universe speaks in the language of calculus, and once you begin to hear it, you'll notice its voice everywhere. Tonight, as your eyes grow heavy and your breathing slows, remember that you're surrounded by mathematical beauty. The rate at which your body temperature adjusts to your environment, the way your heart rate gradually decreases as you relax, the gentle curves that light traces as it dims in your room, all of these follow the elegant principles discovered by Newton and Leibniz over 3 centuries ago. Calculus isn't just an abstract mathematical subject, it's the hidden poetry of change that surrounds us every moment of every day. Let's explore what happens when we slow down and really examine a single moment of change. Imagine you're watching a raindrop slide down a window pane. At first glance, it seems to move at a constant speed. But if you look more carefully, you notice something beautiful happening. The drop doesn't move uniformly. It accelerates as gravity pulls it downward, but but it also experiences resistance from the glass surface. Sometimes it pauses, building up just enough momentum to overcome surface tension, then suddenly lurches forward before settling into a new rhythm. This single raindrop contains within its journey all the fundamental concepts of calculus. Its position on the window is constantly changing, and the rate of that change, its velocity, is also constantly changing. The rate at which the velocity changes, its acceleration, depends on the complex interplay of forces acting upon it. To truly understand the motion of this raindrop, we need to think about instantaneous rates of change, the mathematical concept that lies at the heart of differential calculus. But what exactly does instantaneous mean? In everyday language, an instant is the briefest possible moment, almost zero time. But mathematically, we can't just set time to zero and expect to get a meaningful answer about speed. If a raindrop travels zero distance in zero time, we get the unhelpful result of zero divided by zero. The brilliant insight of calculus is to approach this problem indirectly, by looking at what happens as we consider smaller and smaller time intervals, getting closer and closer to the instant we're interested in without ever quite reaching it. This approach, called taking a limit, is one of the most elegant ideas in all of mathematics. It allows us to talk precisely about things that seem impossible to pin down directly. We can't measure the exact speed of the raindrop at a single instant, but we can measure its average speed over very small time intervals. And as those intervals get smaller, the average speed approaches a specific value. That value is what we call the instantaneous speed, or more formally, the derivative of position with respect to time. Think of it like trying to find the exact color of a sunset. You can't point to a single moment and say there, that's when the sky changed from orange to red. Instead, you observe the gradual transition, noting how the colors shift continuously. The instantaneous color at any moment is the limit of the colors in increasingly small neighborhoods around that moment. Similarly, the instantaneous rate of change is the limit of average rates of change over increasingly small intervals. This concept of limits extends far beyond motion and into every area where things change continuously. When a doctor monitors a patient's heart rate, they're looking at how quickly the heart beats at any given moment. But heart rate isn't constant, it varies based on stress, activity, and countless other factors. The doctor needs to understand not just the heart rate itself, but how quickly it's changing. Are the intervals between beats getting longer or shorter? How rapidly is the patient's cardiovascular system responding to medication? These questions require thinking about rates of change. Concepts that would have been nearly impossible to analyze before calculus. Consider the growth of a tree in your backyard. On any given day, you can't see the tree growing, but over months and years, its height increases dramatically. The tree doesn't grow at a constant rate, though it grows faster in spring and summer when sunlight is abundant and temperatures are warm, and more slowly in fall and winter. Young trees grow faster than old trees. Trees grow faster when they have plenty of water and nutrients, and slower during drought years. The tree's height as a function of time traces out a curve, and the steepness of that curve at any point tells us how fast the tree is growing at that moment. But the story doesn't end with just understanding how fast the tree grows. We might also want to know how the growth rate itself changes over time. Is the tree accelerating its growth, maintaining a steady growth rate, or beginning to slow down as it matures? This requires us to look at the rate of change of the growth rate, what mathematicians call the second derivative. The concepts keep building on each other, creating richer and more nuanced descriptions of how things change in the world around us. The same mathematical principles apply to population growth. Whether we're talking about bacteria in a petri dish, rabbits in a meadow, or people in a city, population doesn't typically grow at a constant rate. Instead, it often follows patterns that can be described by differential equations, mathematical statements that relate a population to its rate of change. A small population might grow slowly simply because there aren't many individuals to reproduce. As the population increases, growth accelerates because there are more potential parents. But eventually, the population might hit environmental limits, and growth slows again as resources become scarce. These population dynamics play out in countless ways in the natural world. Forest fires spread in patterns that can be modeled using calculus, with the rate of spread depending on factors like wind speed, fuel density, and moisture content. Epidemiologists use similar mathematical models to understand how diseases spread through populations, helping public health officials decide when and where to implement interventions. The COVID-19 pandemic brought these concepts into sharp focus, as people around the world learned to interpret graphs showing rates of infection, hospitalization, and recovery. Even in the digital realm, calculus governs much of what we experience. When you watch a video online, compression algorithms use mathematical techniques related to calculus to reduce file sizes while maintaining quality. These algorithms analyze how pixel values change across space and time, identifying redundancies and patterns that can be encoded more efficiently. The smooth gradients you see in digital photographs, the realistic lighting in computer graphics, and the seamless transitions in animated movies all rely on mathematical principles that emerged from the study of continuous change. Machine learning, the technology behind recommendation systems, voice recognition, and autonomous vehicles, is fundamentally rooted in calculus. These systems learn by adjusting millions or billions of parameters to minimize the difference between their predictions and desired outcomes. The process of finding the optimal parameter values involves calculating gradients, multidimensional versions of derivatives that point in the direction of steepest change. Every time your phone's camera automatically focuses or your music app suggests a song you might like, calculus is working behind the scenes. As you settle deeper into comfort tonight, perhaps you can sense this hidden mathematical symphony playing around you, the way your muscles gradually relax, the gentle rhythm of your breathing, the slow cooling of the room as night deepens. All of these follow the beautiful patterns of continuous change that calculus was designed to describe. Mathematics isn't separate from the natural world. It's the language in which the natural world expresses itself, and calculus, with its focus on change and accumulation, speaks most directly to the dynamic, ever-shifting reality of life itself. The story of calculus is also the story of human curiosity and ingenuity. For centuries, people observed change all around them, but lacked the mathematical tools to describe it precisely. The development of calculus represented a breakthrough in human understanding, a new way of thinking about the world that has enabled countless technological advances and scientific discoveries. From the bridges you drive across to the satellites that enable GPS navigation, from the medicines that treat disease to the computer processors that power modern life, calculus has played a crucial role in shaping the world we inhabit. But beyond its practical applications, calculus offers something more profound, a way of seeing. Once you understand the concepts of derivatives and integrals, you begin to notice the patterns of change and accumulation everywhere. You see them in the way morning light gradually fills a room, in the way crowds gather and disperse, in the way seasons transition from one to another. You develop an appreciation for the mathematical elegance underlying apparently chaotic phenomena. You begin to understand that the universe has a deep mathematical structure, one that humans have only begun to explore. Let's take a moment to appreciate how calculus helps us understand one of the most fundamental aspects of existence: growth. Growth is everywhere in nature, from the spiral shells of nautiluses to the branching patterns of rivers and blood vessels. But growth isn't uniform or predictable. It follows patterns that can seem random until we apply the right mathematical tools to understand them. Consider a simple example: a savings account earning compound interest. If you deposit money in an account that earns 5% interest annually, compounded continuously, how much will you have after a certain number of years? This might seem like a straightforward percentage calculation, but it's actually a beautiful example of exponential growth. One of the most important patterns in calculus, the key insight is that the rate at which your money grows is proportional to how much money you currently have. The more money in the account, the more interest it earns, which means even more money to earn interest on. This pattern, where the rate of change is proportional to the current amount, appears throughout nature. Bacterial populations often grow this way when resources are abundant. Each bacterium reproduces at a certain rate, so the more bacteria you have, the faster the population grows. Radioactive decay follows the opposite pattern: exponential decay, where the rate of decrease is proportional to the current amount. Cancer cells, unfortunately, often exhibit exponential growth patterns, which is why early detection and treatment are so crucial. But real-world growth is rarely purely exponential. Resources become limited, competition increases, and growth rates slow down. This leads to what's called logistic growth, where the growth rate starts high when the population is small, reaches a maximum at some intermediate population size, then slows as the population approaches the carrying capacity of its environment. The mathematical curve that describes this process, called a logistic function, appears in context ranging from the adoption of new technologies to the spread of viral social media posts. These growth patterns help explain phenomena that might otherwise seem mysterious. Why does a new social media platform seem to explode in popularity almost overnight, then plateau? Why do forest fires start small but can quickly become massive, then eventually burn themselves out? Why does learning a new skill feel rapid at first, then slow down as you advance? In each case, we're seeing different phases of growth patterns that calculus helps us understand and predict. The mathematics of growth also reveals why compound effects are so powerful over long periods. A small but consistent improvement, repeated over time, can lead to dramatic changes. This principle applies whether we're talking about earning interest on investments, developing skills through practice, or building habits that gradually transform our lives. The key is understanding that growth builds on itself, creating feedback loops that can be either virtuous or vicious depending on the direction of change. In the realm of physics, calculus revealed some of the most profound truths about our universe. When Newton applied his new mathematical tools to the problem of planetary motion, he discovered that the same force responsible for an apple falling from a tree also keeps the moon in orbit around Earth. This insight that gravitation is a universal force following precise mathematical laws revolutionized our understanding of the cosmos. The elliptical orbits of planets, which had been observed and described by astronomers like Johannes Kepler, suddenly made perfect mathematical sense. But Newton's laws of motion, expressed through differential equations, do much more than explain planetary orbits. They describe the motion of everything from subatomic particles to galaxies. When you throw a ball, fire a rocket, or simply walk down the street, your motion follows patterns that can be predicted using calculus. The trajectory of a baseball accounts for the initial velocity, the acceleration due to gravity, and the resistance of air. The path of a spacecraft traveling to Mars must account for the gravitational influences of multiple planets. These calculations, which would have been impossible before calculus, are now routine. The relationship between position, velocity, and acceleration provides a perfect illustration of how calculus connects different aspects of the same phenomenon. Position tells us where something is. Velocity, the derivative of position, tells us how fast the position is changing. Acceleration, the derivative of velocity, tells us how fast the velocity is changing. These three concepts form a hierarchy of information, each level providing deeper insight into the nature of motion. This hierarchical relationship extends beyond motion to many other areas. In economics, we might be interested in total wealth, the rate at which wealth changes, income, and the rate at which income changes, economic growth or decline. In medicine, we might track a patient's temperature, the rate at which temperature changes, and whether that rate itself is increasing or decreasing. In environmental science, we might monitor carbon dioxide levels in the atmosphere, the rate at which those levels are rising, and whether the rate of increase is accelerating or slowing down. Understanding these relationships helps us make better predictions and decisions. A doctor who notices that a patient's fever is not just high, but rising at an increasing rate, might take more aggressive action than if the fever were high, but stable. An investor who sees that a company's profits are not just growing, but growing at an accelerating rate, might make different investment decisions than if profits were growing at a steady pace. These kinds of insights emerge naturally when we think in terms of derivatives and rates of change. The concept of optimization, finding the best possible outcome among many alternatives, represents another beautiful application of calculus. In your daily life, you're constantly making optimization decisions, even if you don't think of them in mathematical terms. When you choose the fastest route to work, you're solving an optimization problem. When you adjust the temperature in your home to balance comfort and energy costs, you're finding an optimal compromise. When you decide how to allocate your time between different activities, you're optimizing your personal satisfaction and productivity. Calculus provides systematic methods for solving optimization problems that would be impossible to handle through trial and error. The key insight is that optimal solutions often occur at points where the rate of change is zero. Think of rolling a ball over a hilly landscape. The ball will naturally come to rest at the bottom of a valley, where the slope in every direction is zero. Similarly, many optimization problems can be solved by finding points where the derivative equals zero. This principle has applications ranging from the mundane to the profound. Engineers use optimization to design bridges that can support maximum weight with minimum material. Airlines use it to schedule flights and price tickets to maximize revenue. Doctors use it to determine optimal drug dosages that maximize therapeutic benefit while minimizing side effects. Even evolution can be thought of as a vast optimization process, where natural selection gradually improves the fit between organisms and their environments. Sometimes the most elegant solutions emerge from the simplest mathematical principles. The Brechster-Krone problem, first posed by Johann Bernoulli in 1696, asks what is the fastest path for a ball to roll from one point to another under the influence of gravity. Intuitively, you might think the fastest path would be a straight line, since that's the shortest distance, but calculus reveals that the optimal path is actually a curve called a cycloid, where the ball gains speed quickly by dropping steeply at first, then maintains that speed over a more gradual descent. This counterintuitive result illustrates one of the most valuable aspects of mathematical thinking. It can reveal truths that contradict our initial assumptions. The natural world is full of such surprises. Soap bubbles automatically form shapes that minimize surface area for a given volume, creating beautiful spherical and more complex geometries. Light traveling through materials of different densities follows paths that minimize travel time, creating the phenomenon of refraction. Birds and aircraft achieve maximum efficiency by adjusting their flight patterns in ways that can be described using calculus of variations. The mathematics of optimization also helps us understand trade-offs, situations where improving one aspect of a system necessarily means accepting compromises in another. In engineering, stronger materials are often heavier, so designing an airplane requires balancing strength against weight. In economics, higher returns on investments typically come with higher risks. In ecology, organisms that reproduce quickly often have shorter lifespans. Calculus provides tools for analyzing these trade-offs systematically and finding the combinations that achieve the best overall outcomes. As you lie there listening to this, your body is continuously solving optimization problems without your conscious awareness. Your heart adjusts its rate to pump just enough blood to meet your current oxygen needs. Your pupils dilate or contract to optimize the amount of light entering your eyes. Your breathing automatically adjusts to maintain the right balance of oxygen and carbon dioxide in your bloodstream. These biological control systems, honed by millions of years of evolution, demonstrate optimization principles that engineers now try to replicate in artificial systems. The integration half of calculus, often considered more challenging than differentiation, deals with accumulation and area. While derivatives answer questions about rates of change, integrals answer questions about totals. How much distance did you travel during a trip where your speed varied continuously? How much water flows through a pipe over a period of time when the flow rate changes? How much energy does a variable electrical current deliver? These questions all require integration, the process of adding up infinitely many infinitesimally small pieces. One of the most intuitive ways to understand integration is through the concept of area under a curve. If you have a graph showing how your car's speed changes over time during a trip, the area under that speed curve tells you the total distance you traveled. This connection between area and accumulation extends to countless other situations. The area under a graph of power consumption tells you total energy used. The area under a graph of rainfall rate tells you total precipitation. The area under a graph of production rate tells you total output. But integration goes far beyond simple area calculations. It provides tools for solving complex problems in physics, engineering, economics, and many other fields. When engineers design a dam to calculate the total force exerted by water pressing against the structure, this force varies with depth. Since water pressure increases the deeper you go, integration allows them to add up the contributions from each small section of the dam wall to find the total force. Without these calculations, dams could fail catastrophically. In medicine, integration helps determine proper drug dosages for patients with varying metabolisms. Different people process medications at different rates, and the same person might process a drug differently depending on their current health status. By modeling how drug concentration changes over time in the bloodstream, doctors can calculate the optimal timing and dosage to maintain therapeutic levels without reaching toxic concentrations. These calculations literally save lives by ensuring patients receive neither too little nor too much medication. The fundamental theorem of calculus creates a beautiful connection between derivatives and integrals, showing that these two processes are mathematical inverses of each other. If you start with a function, take its derivative, then integrate the result, you get back to where you started plus possibly a constant. This relationship is more than just a mathematical curiosity. It provides powerful computational tools and reveals deep connections between apparently different phenomena. This inverse relationship appears throughout the physical world. If you know how the velocity of an object changes over time, you can integrate to find its position. If you know how position changes over time, you can differentiate to find velocity. If you know how electric field strength varies through space, you can integrate to find electric potential. If you know potential, you can differentiate to find field strength. These dual descriptions give us multiple ways to approach the same physical situation, often revealing insights that wouldn't be apparent from just one perspective. The elegance of calculus lies not just in its individual concepts, but in how those concepts work together to create a unified mathematical language for describing change and accumulation. Differential equations, which relate functions to their derivatives, allow us to model dynamic systems where the rate of change depends on the current state. These equations describe everything from the oscillation of a pendulum to the fluctuations of stock markets, to the chemical reactions in living cells. Solving differential equations often requires combining multiple calculus techniques in creative ways. You might need to use substitution methods reminiscent of algebra, integration techniques that transform complex expressions into simpler forms, or series expansions that approximate complicated functions with polynomial expressions. The interplay between these different mathematical tools creates a rich problem-solving environment where multiple approaches might lead to the same solution, or where different techniques might reveal different aspects of the underlying phenomenon. Some of the most beautiful mathematics emerges when we consider systems with multiple variables changing simultaneously. Partial derivatives allow us to examine how a function changes with respect to one variable while holding others constant. This is crucial for understanding phenomena like weather patterns, where temperature, pressure, humidity, and wind speed all influence each other in complex ways. Meteorologists use partial differential equations to model these interactions and generate the weather forecasts that help you decide whether to bring an umbrella tomorrow. The mathematics of several variables also underlies much of modern technology. When your smartphone's camera automatically adjusts focus, exposure, and white balance, it's solving optimization problems in a multidimensional space where changing one setting affects the optimal values for others. When GPS systems calculate routes, they're navigating through spaces where travel time depends on multiple factors including distance, traffic density, road conditions, and time of day. The algorithms that power search engines analyze billions of web pages using techniques that extend calculus concepts to incredibly high-dimensional spaces. Vector calculus extends these ideas even further, providing tools for analyzing fields and flows. When you see weather maps showing wind patterns with arrows indicating both speed and direction, you're looking at vector fields. The mathematics of vector calculus helps meteorologists understand how these patterns evolve over time, how energy moves through the atmosphere, and how different air masses interact to create storms and other weather phenomena. The same mathematical framework describes electromagnetic fields, gravitational fields, and fluid flows. When engineers design airplane wings, they analyze how air flows around the wing surfaces using vector calculus. When medical researchers study blood flow through arteries, they use similar mathematical tools to understand how vessel shape affects circulation. When astrophysicists model the formation of galaxies, they apply vector calculus to understand how gravitational and electromagnetic forces shape the large-scale structure of the universe. Perhaps most remarkably, the mathematical tools developed to study change and accumulation have revealed unexpected connections between seemingly unrelated phenomena. The same differential equations that describe the oscillation of a spring also describe the behavior of electrical circuits with inductors and capacitors. The mathematics of heat diffusion through a metal rod also applies to the spread of rumors through social networks and the pricing of financial options. The equations governing wave motion in water also describe the propagation of light, sound, and quantum mechanical wave functions. These connections suggest something profound about the nature of mathematics and reality. The universe seems to operate according to a relatively small number of fundamental patterns, which manifest in countless different contexts. Calculus provides a language for recognizing and working with these patterns, allowing us to transfer insights from familiar situations to unfamiliar ones. When medical researchers want to understand how cancer spreads through tissue, they can draw on mathematical techniques, originally developed to study fluid dynamics. When economists model market volatility, they use tools borrowed from physics. The history of calculus also illustrates how mathematical discoveries often emerge from practical needs, then find applications far beyond their original purposes. Newton developed calculus primarily to solve problems in physics and astronomy, but the mathematical tools he created have since found applications in every field that deals with quantitative change. Leibniz was motivated by philosophical questions about the nature of continuous versus discrete phenomena, but his mathematical notation and concepts now power computer graphics, medical imaging, and artificial intelligence. This pattern continues today as researchers develop new mathematical techniques to solve contemporary problems, then discover that these techniques have unexpected applications in completely different fields. Mathematics developed for analyzing financial markets has found applications in epidemiology. Techniques created for processing digital images have been applied to analyzing biological datasets. Methods for optimizing supply chains have been adapted to study ecological food webs. The universality of mathematical patterns suggests that learning calculus isn't just about acquiring a set of computational tools, it's about developing a new way of seeing the world. Once you understand derivatives and integrals, you begin to notice rates of change and accumulations everywhere. You see them in the gradual brightening of dawn, the way coffee shops fill and empty throughout the day, the seasonal cycles of plant growth and dormancy. You develop an appreciation for the mathematical structure underlying natural phenomena, and you begin to understand why mathematics has been called the language of the universe. This mathematical perspective doesn't diminish the beauty or mystery of the world. Rather, it adds another layer of appreciation. Understanding the physics of how rainbows form doesn't make them less beautiful, it makes them more wonderful by revealing the elegant interplay of light, water, and geometry that creates those perfect arcs of color. Similarly, understanding the mathematical patterns in music doesn't reduce its emotional impact. It helps explain why certain combinations of notes create harmony while others create tension. As mathematical tools have become more sophisticated, they've enabled us to tackle increasingly complex problems that affect human welfare. Climate scientists use advanced calculus-based models to understand how greenhouse gas emissions might affect global temperatures over decades and centuries. These models consider thousands of interacting variables, from ocean currents to cloud formation to vegetation patterns, and they require some of the most powerful computers in the world to solve the resulting differential equations. Medical researchers use similar mathematical approaches to understand how diseases progress and how treatments might work. When pharmaceutical companies test new drugs, they use mathematical models to predict how the drugs will be absorbed, distributed, metabolized, and eliminated by the human body. These pharmacokinetic models, based on differential equations, help determine appropriate dosages and identify potential safety concerns before drugs reach patients. In engineering, calculus-based analysis has enabled the construction of structures that would have been impossible without mathematical understanding of stress, strain, and material behavior. Modern skyscrapers can withstand earthquakes because engineers use sophisticated mathematical models to predict how buildings will respond to ground motion. Bridges can span enormous distances because mathematical analysis reveals optimal designs that balance strength, weight, and cost. The digital revolution has been powered by mathematical advances that build on calculus foundations. Computer graphics rely on mathematical descriptions of curves, surfaces, and lighting effects. Signal processing, which enables everything from digital music to medical imaging to satellite communications, uses mathematical techniques related to integration and differentiation. Machine learning algorithms that power recommendation systems, speech recognition, and autonomous vehicles all rely on optimization methods that trace their roots back to the calculus of variations. Yet, despite its enormous practical importance, perhaps the greatest gift of calculus is the perspective it provides on the nature of change itself. In a world where everything is constantly shifting and evolving, calculus offers tools for making sense of dynamic phenomena. It helps us distinguish between different types of change, linear change that proceeds at a constant rate, exponential change that decelerates over time, oscillatory change that repeats in cycles, and chaotic change that appears random but follows deterministic rules. Understanding these different patterns of change can be profoundly useful in personal life as well as professional contexts. When you're learning a new skill, recognizing that progress often follows a logistic growth pattern can help you maintain motivation during the inevitable plateau phases. When you're saving for a long-term goal, understanding exponential growth can help you appreciate the power of starting early and contributing consistently. When you're trying to break a bad habit or establish a good one, understanding the mathematics of feedback loops can help you design more effective strategies. The concepts of calculus also provide metaphors for understanding psychological and social phenomena. The idea of a derivative, a rate of change, helps us think about momentum in our personal lives. Are our relationships, careers, or health improving or declining? How quickly? The idea of an integral, an accumulation over time, helps us think about the long-term consequences of our daily choices. Small positive actions, repeated consistently, can lead to significant improvements over time, just as small negative actions can accumulate into serious problems. The optimization perspective from calculus encourages us to think systematically about trade-offs and to look for solutions that balance competing objectives. Instead of seeking perfect solutions that don't exist, we can look for optimal solutions that make the best possible compromises among conflicting goals. This mindset can be valuable whether you're planning a career, managing a household budget, or deciding how to spend your limited time and energy. The mathematical concept of limits offers a way of thinking about goals and aspirations. We might not be able to achieve perfection directly, but we can often get arbitrarily close by making continuous improvements. The limit concept suggests that the journey toward a goal can be as important as reaching the destination, because each step in the right direction brings us closer to where we want to be. Even if we never quite arrive at some idealized endpoint, this perspective can be particularly comforting when dealing with personal growth and change. Instead of expecting immediate transformation, we can focus on consistent progress in the right direction. The mathematical intuition behind limits tells us that small, steady improvements can eventually lead to dramatic changes, just as a sequence of numbers can approach a limit through tiny incremental steps. Whether you're working to improve your health, develop new skills, or strengthen relationships, the calculus mindset encourages patience and persistence over perfectionism. The study of calculus also reveals the importance of understanding context and scale. A function that grows rapidly over a short time interval might level off or even decline over longer periods. A rate of change that seems significant at one scale might be negligible at another. This mathematical insight translates into wisdom about evaluating changes in our personal and professional lives. A temporary setback doesn't necessarily indicate a negative long-term trend, just as a brief period of rapid progress doesn't guarantee continued success at the same rate. These mathematical perspectives can help us develop more nuanced and realistic expectations about change in our lives. Instead of expecting linear progress toward our goals, we can anticipate that improvement often comes in waves, with periods of rapid advancement followed by plateaus or even temporary reversals. Understanding these patterns can help us maintain motivation during difficult periods and avoid complacency during easy ones. The interconnectedness revealed by calculus also offers insights into how different aspects of our lives influence each other. Just as changing one variable in a multivariable function affects the optimal values of other variables, changes in one area of life often have ripple effects in other areas. Improving your physical health might boost your mental clarity and work performance. Developing better time management skills might improve both your professional productivity and your personal relationships. Calculus encourages us to think systematically about these connections rather than treating different life domains as completely separate. But let's step back from these philosophical applications and appreciate calculus for what it fundamentally is, a celebration of change itself. In a universe where nothing stays the same, where planets orbit stars, where seasons cycle endlessly, where living things grow and evolve and eventually return to the Earth, calculus provides a language for embracing and understanding the dynamic nature of existence. It teaches us that change isn't something to be feared or resisted, but something to be studied, appreciated, and worked with skillfully. The mathematical beauty of calculus lies partly in its ability to find patterns and order within apparent chaos. A leaf falling from a tree follows a complex path influenced by air currents, its own rotating motion, and constantly changing forces. Yet this seemingly random motion can be described precisely using differential equations. A stock market that appears to fluctuate unpredictably actually follows mathematical patterns that can be analyzed using sophisticated calculus-based models. Even quantum mechanics, the strange world of subatomic particles, relies on mathematical tools that extend classical calculus into new realms. This ability to find mathematical structure in complex phenomena has profound implications for how we understand our place in the universe. Rather than seeing ourselves as separate from the natural world, calculus reveals that we are part of the same mathematical tapestry that governs everything from galaxies to electrons. The same principles that describe planetary motion also describe the circulation of blood through our bodies. The same equations that model population growth in ecosystems also model the spread of ideas through human cultures. This mathematical unity suggests that there are deep connections between all phenomena, connections that become visible when we learn to see the world through mathematical eyes. Calculus doesn't just describe change, it reveals the fundamental relationships that connect different types of change to each other. The rate at which a river flows is connected to the shape of its bed, which in turn affects the rate of erosion, which gradually changes the shape of the landscape. These feedback loops and interconnections create the rich, dynamic systems that make up our world. Understanding these connections can foster a sense of wonder and appreciation for the complexity and elegance of natural systems. When you watch waves breaking on a beach, you're seeing the result of energy that might have traveled thousands of miles across the ocean, shaped by wind patterns, ocean currents, and the gravitational pull of the moon. The mathematical equations that describe wave motion help reveal the hidden connections between local phenomena and global systems. Similarly, when you listen to music, you're experiencing mathematical relationships between different frequencies of sound waves. The harmony and discord in music reflect mathematical ratios that have been studied since ancient times, but calculus provides tools for analyzing more complex musical phenomena like how different instruments blend together or how electronic music can create entirely new types of sounds through mathematical manipulation of waveforms. The applications of calculus continue to expand as we develop new technologies and encounter new challenges. Climate change, for instance, requires mathematical models that can integrate information about atmospheric chemistry, ocean dynamics, ice sheet behavior, vegetation patterns, and human activities. These models use some of the most advanced calculus-based techniques ever developed, running on supercomputers that perform trillions of calculations to simulate how Earth's climate system might evolve over the coming decades. Artificial intelligence represents another frontier where calculus plays a crucial role. Machine learning algorithms learn by adjusting millions or billions of parameters to minimize prediction errors, a process that relies heavily on multivariable calculus and optimization theory. When your phone recognizes your voice, when your car's navigation system suggests a route, or when an online service recommends a product you might like, calculus-based algorithms are working behind the scenes to process vast amounts of data and identify meaningful patterns. Medical imaging provides another compelling example of how calculus continues to transform human capabilities. CT scans, MRI images, and ultrasounds all rely on mathematical techniques that reconstruct internal body structures from external measurements. These reconstruction algorithms use sophisticated integration techniques to build three-dimensional images from thousands of individual data points. The result is that doctors can see inside the human body with unprecedented clarity, enabling earlier diagnosis and more precise treatments. The mathematical principles underlying these technologies often involve concepts that extend far beyond basic calculus, but they all build on the fundamental ideas of derivatives, integrals, and differential equations. Understanding these basic concepts provides a foundation for appreciating the mathematical sophistication of modern technology. Even if the detailed calculations require specialized knowledge and powerful computers, perhaps most remarkably, calculus continues to reveal new insights about the universe at both the largest and smallest scales. Einstein's theories of relativity, which revolutionized our understanding of space, time, and gravity, are formulated using advanced calculus techniques, These theories predict phenomena like time dilation, where time passes differently for objects moving at high speeds or in strong gravitational fields. Such effects were pure mathematical speculation when Einstein first proposed them, but they've since been confirmed by countless experiments and are now essential for technologies like GPS satellites. At the quantum scale, the mathematics becomes even more abstract, involving complex numbers, infinite dimensional spaces, and probability amplitudes. Yet these exotic mathematical structures still build on the basic calculus concepts of derivatives and integrals, extended into new mathematical territories. The Schrödinger equation, which describes how quantum systems evolve over time, is fundamentally a differential equation, though it operates in a mathematical space quite different from our everyday experience. These cutting-edge applications might seem far removed from daily life, but they actually touch our lives in countless ways. The computer or phone you're using to listen to this relies on quantum mechanical principles that are described using advanced mathematics. The GPS system that helps you navigate uses relativistic corrections that require sophisticated calculus calculations. The medical technologies that extend and improve human lives depend on mathematical models of biological processes. Even when we're not directly using these technologies, we benefit from the scientific understanding they enable. Weather forecasts that help farmers plan their planting and harvesting rely on atmospheric models based on fluid dynamics equations. Earthquake engineering that makes buildings safer uses mathematical analysis of how structures respond to ground motion. Drug development that brings new treatments for diseases relies on mathematical models of how molecules interact with biological systems. The ongoing development of calculus and its applications represents one of humanity's greatest intellectual achievements. Starting from simple questions about motion and change, mathematicians have built a framework that now enables us to understand phenomena ranging from the behavior of individual atoms to the evolution of entire galaxies. This mathematical toolkit continues to grow as new problems demand new techniques and new technologies enable previously impossible calculations. Yet despite its sophistication and power, calculus remains fundamentally grounded in intuitive ideas about change and accumulation that anyone can understand. The concept of a derivative as an instantaneous rate of change connects directly to everyday experiences of motion, growth, and variation. The concept of an integral as accumulated change connects to familiar ideas about adding up small contributions over time. These intuitive foundations mean that anyone can develop at least a basic appreciation for calculus concepts, even without mastering the computational techniques. This accessibility is important because calculus concepts are increasingly relevant for making sense of the modern world. Understanding exponential growth helps interpret everything from pandemic spread to investment returns to technological progress. Understanding optimization helps make better decisions in situations involving trade-offs and constraints. Understanding feedback loops and differential equations helps recognize patterns in complex systems, whether they're ecological, economic, or social. As our world becomes increasingly quantitative and data-driven, mathematical literacy becomes increasingly important for full participation in society. This doesn't mean everyone needs to become a professional mathematician, but it does mean that basic mathematical concepts like those found in calculus can enhance our ability to understand and engage with important issues. Whether you're evaluating health advice, making financial decisions, or trying to understand policy debates about climate change, some familiarity with mathematical thinking can be genuinely helpful. The beauty of calculus education lies not just in learning specific techniques, but in developing mathematical habits of mind that can be applied broadly. Learning to think about rates of change encourages attention to trends and patterns over time. Learning to think about optimization encourages systematic consideration of trade-offs and constraints. Learning to think about limits encourages appreciation for processes that approach goals gradually rather than achieving them instantaneously. These mathematical habits of mind can enhance problem-solving abilities in many contexts beyond traditional mathematical applications. When facing a complex decision, the calculus mindset encourages breaking the problem down into smaller pieces, looking for patterns and relationships, and considering how different factors influence each other. When evaluating claims or arguments, mathematical thinking encourages attention to quantitative evidence and logical consistency. Perhaps most importantly, studying calculus can foster a sense of intellectual humility and wonder. The more you learn about mathematics, the more you realize how much remains unknown and how many deep questions are still unsolved. This perspective can be refreshing in a world where confident assertions and simple answers are often valued over careful analysis and nuanced understanding. The ongoing research frontiers in mathematics continue to reveal new applications and deeper insights. Mathematicians are developing new techniques for analyzing high-dimensional data, understanding network structures, and modeling complex adaptive systems. These advances are finding applications in fields ranging from neuroscience to social media analysis to personalized medicine. The mathematical toolkit that began with Newton and Leibniz continues to grow and evolve, suggesting that we've only begun to explore the full potential of mathematical approaches to understanding change and accumulation. As you settle more deeply into relaxation tonight, perhaps you can appreciate the mathematical symphony playing around you. The gentle rhythm of your breathing follows patterns that can be described using trigonometric functions. The gradual cooling of your room involves heat transfer processes governed by differential equations. The electronic devices around you operate according to principles that require sophisticated mathematical analysis to understand fully. But you don't need to understand all the mathematical details to appreciate the elegant patterns that govern natural phenomena. The key insight of calculus is that change and accumulation, the most fundamental processes in the universe, can be understood systematically using mathematical tools. Whether we're talking about the motion of planets, the growth of living things, the flow of energy, or the spread of information, the same basic mathematical principles apply. This universality of mathematical principles suggests something profound about the nature of reality itself. The fact that diverse phenomena can be described using the same mathematical language implies deep connections between apparently different aspects of the world. The equations that describe how heat flows through a metal rod also describe how rumors spread through social networks. The mathematics of wave motion applies equally to sound waves, light waves, and quantum mechanical wave functions. These connections reveal that mathematics is not an arbitrary human invention, but rather a language for describing real patterns that exist in the world. When mathematicians discover new theorems or develop new techniques, they're not creating something from nothing, they're uncovering relationships and structures that were always there, waiting to be found. This perspective can foster a sense of awe and respect for the mathematical order underlying natural phenomena. The historical development of calculus also illustrates how mathematical understanding often emerges gradually through the work of many individuals over long periods of time. While we associate calculus with Newton and Leibniz, their discoveries built on earlier work by mathematicians like Fermat, Descartes, and others, and the full implications of their insights took centuries to develop. Even today, mathematicians continue to find new applications and discover new connections that the original inventors never anticipated. This ongoing development suggests that our current understanding of calculus and its applications represents just one chapter in a much longer story. Future generations of mathematicians and scientists will undoubtedly find new ways to extend and apply these mathematical tools, just as current researchers have found applications that Newton and Leibniz could never have imagined. The mathematical framework they created has proven remarkably robust and flexible, continuing to yield new insights and applications centuries after its initial development. The collaborative nature of mathematical progress also reflects something important about human knowledge more generally. Scientific and mathematical understanding advances through the cumulative efforts of many individuals, each contributing their own insights and perspectives to a growing body of knowledge. This collaborative aspect means that mathematical discoveries belong not to individual geniuses, but to humanity as a whole. This perspective can be both humbling and inspiring. It reminds us that each generation builds on the work of previous generations, and that our own contributions, however small, become part of the foundation for future discoveries. Whether you're a professional mathematician or simply someone trying to understand the world a little better, you're participating in this ongoing collective effort to understand the patterns and relationships that govern natural phenomena. As your eyelids grow heavier and the world around you settles into the quiet rhythms of night, take a moment to appreciate the mathematical elegance that surrounds you. The steady beating of your heart follows patterns that can be analyzed using calculus. The way your body temperature adjusts to changes in your environment involves feedback mechanisms that can be modeled using differential equations. Even your dreams, which you'll soon experience, emerge from neural processes that scientists are beginning to understand using sophisticated mathematical tools. The boundary between mathematics and reality becomes blurred when you realize that mathematical patterns aren't just abstract concepts, but actual descriptions of how the world works. The curves described by mathematical functions are the same curves traced by falling leaves, orbiting planets, and oscillating pendulums. The rates of change calculated using derivatives are the same rates of change that govern the spread of diseases, the growth of populations, and the flow of heat through materials. This deep connection between mathematics and reality suggests that learning about calculus isn't just an academic exercise, but a way of developing a deeper relationship with the natural world. Understanding mathematical patterns can enhance your appreciation for the elegance and complexity of natural phenomena, from the spiral patterns in seashells to the fractal structures in clouds to the wave patterns in flowing water. The mathematical perspective also encourages a sense of wonder about the universe itself. The fact that complex phenomena can be described using relatively simple mathematical principles suggests an underlying order and harmony that many people find deeply moving. This mathematical order doesn't diminish the mystery and beauty of natural phenomena. Instead, it adds another layer of appreciation by revealing the elegant principles that govern change and growth throughout the universe. Tonight, as calculus and its many applications fade into the background of consciousness, remember that you are part of this mathematically ordered universe. The same principles that govern the motion of galaxies also govern the circulation of blood through your veins. The same mathematical relationships that describe the growth of forests also describe the development of your own body and mind. You are not separate from the mathematical patterns that surround you, you are an expression of them. Sleep well, knowing that the universe continues its ancient mathematical dance around you, following patterns established billions of years ago and continuing into an infinite future of change, growth, and discovery. The calculus that describes this cosmic dance is not just an abstract theory, but the very language in which the story of existence is told.